In Lesson 1, I waxed lyrically about the advantages of deep learning approaches for natural language processing. In particular, I described that the strength and flexibility of deep learning NLP models is a consequence of them storing the elements of language, often as is the case in these live lessons, words, in a vector space. Now the time has arrived for us to discuss these word vectors in detail. A great quote to describe how word vectors are created is from J.R. Firth in 1957. He says, "You shall know a word by the company it keeps." We'll come back to that in a second. But the idea initially proposed earlier by Ludwig Wittgenstein is that the meaning of a given word can be represented by the words around it. So in our 3D cube here, which I always draw when I'm explaining word vectors or n-dimensional space, we have in our vector spaces that we'll be building, we'll typically have at least 25 dimensions, typically more like 256 or 300 or 512 dimensions. And the most advanced applications that leverage the largest, richest natural language data sets will have 1,000 or more dimensions. But for the sake of our simple human brains, we'll stick with a 3-dimensional n-dimensional space. So represented by the x, y, and z axes here. So in this n-dimensional space, synonyms and common misspellings, because they share an identical meaning, should have near identical coordinates. So you'd have dots that are in essentially the exact same space. Closely related words to a given word should have nearby coordinates and therefore share a pretty similar space. So some good examples of that could be days of the week, Monday, Tuesday, Wednesday. These should be very close to each other. And so maybe we have a cluster over here of days of the week, Monday, Tuesday, Wednesday in brown. And then nearby, we're very likely to find other kinds of temporal things forming their own cluster. So months of the year, January, February, March. These will have very close together coordinates for each of the month, and they'll probably be somewhere nearby our days of the week cluster. Relevant to these live lessons, you would have somewhere far away from days of the week probably represented object-oriented programming languages like Python, Java, and Ruby. Somewhere else, you'd have Unix shell scripting languages forming their own kind of cluster, Bash, KSH, CSH. They'd be probably near our object-oriented programming languages. Less concretely defined terms, but that nevertheless contain a specific meaning, like created, developed, built. Those kinds of words will also have their own space. This isn't just for very concrete words. So groups of words that are more similar have their own spaces, as we've covered here. And we could be making use of this whole cube, but I'm saving a bit of space for later. So remarkably, the length and direction of a vector within this space can represent a particular real-world attribute. So let's erase these last few dots here. Let's say that we located a spot for man, and somewhere else in this space is represented the word woman. Elsewhere in the space we have king and queen, and somewhere else we have aunt and uncle. the remarkable thing is that there is a particular vector direction and distance within this n-dimensional space that represents gender. So this particular vector, this green vector with this length and this direction, wherever you put it in here, if you find a male word and then you move along this vector, you are likely to find the kind of female equivalent of that word. And this applies to many different kinds of data. So another example would be having words like Paris, France, London, and UK. These words would have a different vector with a particular orientation and length that represents the relationship between capitals and countries. We're going to use this tool here, this Explore Word Analogies tool, in quite a bit of detail in a moment. But I just wanted to show the parallel between what we had on the board and what we have here in the program. This is likewise showing the similar vector and direction and length representing the difference between female and male data points. So you can see the queen and king difference is very similar to the aunt and uncle difference, which is quite similar to the mother-father, the woman-man. And we'll explore this in more detail in a second. So I want to take this one more step further down the mind-boggling road before we get deep into this tool. So check out these examples. Because of the reliability of these vectors, we're able to do vector arithmetic. So the most common example is to say the vector for king. So this vector in our space here, in our three-dimensional space, this is just a vector of length 3, representing the x, y, and z coordinate that king is at. If we subtract from that the vector for man, which is located over here, so we subtract this vector, and then we add the location, the vector location for woman, we end up at this vector location for queen. So that's pretty amazing. It means we can use the meaningful real-world relationships represented within these vectors to traverse over this space. And the examples can get way more abstract than this. So we can have Paris minus France plus Germany equals Berlin. We can have Mark Zuckerberg minus Facebook plus Amazon equals Jeff Bezos. We could do Windows minus Microsoft plus Google equals Android. So it's totally mind-boggling to me, and it's one of the most wonderful things I've ever learned. So let's explore this more deeply and make it concrete. To bring these word vector concepts to life interactively, let's play around with a tool called WordDeviz, built by the University of Warsaw's Julia Basinska. So starting with the gender analogies screen that I introduced a little bit earlier, let's add in a few more words so to see how the relationships work. So businesswoman, businessman, add that pair in. We see that that new pair has the same kind of relationship. We see the same kind of thing, I bet, with princess and prince. Yep. And duchess and duke. So any of these kinds of words work like that. And you can see that along the y-axis, we have kind of commoner type word, woman, through to the royal sounding word queen. So this y-axis represents kind of royalness, and the x-axis from she to he represents gender. Now let's look at another one of these to give a sense of the breadth of applications that word vectors can have. So here are a bunch of adjectives moving from nice to nicest and nicer to nicest. So there are these various darkest, fattest, thinnest, and you can see that they all move in concert together. So along to the left, thin is to the left of thinnest, and fat is to the left of fattest. But we can really throw this for a loop by changing, say, this nicer to nicest axis to thin and fat. Let's see how that affects things. So we still have everything going from moderate, thin and fat, for example, through to thinnest and fattest, but now we have this additional axis dimension representing thin and fat. And we can see that words like big are closer, along this axis towards fat than some of the other words. So let's have a look at another one of these examples. So here's numbers being represented. This is really cool. So we have on the left-hand side the written characters representing each of these numbers, and then on the far right we have the integers representing each of those numbers. And we can play around with this a little more by looking at if we change the x-axis just to integers, if these properties still hold. And of course they do. So pretty cool that all these different kinds of abstract objects in a large enough data set can be represented together. Let's have a look at verb tenses. So even words that have the same meaning but are in a different tense can have a consistent vector relationship demonstrating that. Now, this chart right here also highlights risks of unintentional effects that can happen with any kind of data set that you use. So natural language data sets possess whatever kinds of biases have accrued in that natural language over time. And so, for example, a sexist meaning of gender can be incorporated into an AI model downstream of these vector space embeddings. For example, so some of these words are considered more masculine according to the data. So fail among all these words is considered to be one of the more masculine, or fought, destroy. Meanwhile, words like sing or dance are considered to be more female. So that's something to bear in mind when you're working with any natural language data. There will be biases inherent in it, and so you have to be careful. If we move to the jobs segment, that sexism can be even more explicit. So you can imagine that there are particular roles in here that are associated with being male or female, and those are going to then end up being incorporated into any downstream natural language application that you have. All right, so fair warning when using any natural language data. Now, let's make use of this empty one here and have some fun with it. So let's try to tie together some of the examples that we did on the board. Let's try to do some things with countries and cities here. You guys can play around at home with any particular kinds of words that you want. So let's have our x-axis represent west and east, and then our y-axis can represent city and country. Click Change Axis Labels to have those added to the chart. And then we can start adding in pairs of words. So London, England. Let's see what happens. Okay. Unsurprisingly, the city-country axis is lighting up there. And Paris, France. Add that in as well. There we go. Paris and France are just to the east of London and England. Berlin and Germany. That also works out. And let's try somewhere much further east. Let's try Beijing and China. And that worked out as well. So one critical item to bear in mind here is that a given individual axis of the n-dimensional vector space does not necessarily represent any specific real-world meaning. So here in these word-to-viz examples, we've oriented the dimensions to particular words, but in the kind of raw vector space output that comes out, those orientations aren't necessarily aligned with any real-world concepts. Those real-world concepts could be at other angles within the space. So, for example, although the real-world differences in meaning of gender or verb tense are represented by some vector direction within the vector space, this meaningful vector direction may only be by chance aligned or perhaps correlated with one of the, say, 300 or 1,000 axes of the vector space. This contrasts with other approaches that involve n-dimensional vector spaces like principal component analysis, where the axes are intended to represent some real-world contributor to variance. A corollary or side effect of this difference between information stored as points in principal components analysis versus in a vector space embedding is that in principal component analysis, the first principal components contribute most of the variance, so you can focus on them and ignore later principal components. But in vector space embeddings, all of the dimensions may be important and need to be taken into consideration. Now that we have an intuitive understanding of what word vectors are, I'd like to return to reinforce a few points from earlier in the live lessons regarding the flexibility afforded by vector spaces relative to traditional approaches. As should now be very clear, the power and flexibility of word vectors comes from their continuous smeared nature. The meaning of words is stored in a distributed representation across this n-dimensional space. There's no need for a human to come along and define whether words are related to each other or how a new word's meaning relates to the other established words. Everything is learned from natural language. Prior to these distributional representations of words coming into vogue around 2015, we had only the localist, one-hot representations that I introduced in slide 1 with the cat sat on the mat example. So let's talk about some additional specific problems with this kind of localist representation. So the first thing is that these localist one-hot representations miss nuance. So similar words like hotel or motel are no more closely related than unrelated ones like hotel and dog, whereas that nuance is captured in vector space. The second thing is that new words are not accounted for by one-hot word representations automatically, whereas new words can be added to a vector space provided we have data that includes that new word. The one-hot word representations are subjective. So if using dictionary definitions or a taxonomy like WordNet that annotates synonym sets and hypernyms, is-a relationships like a terrier is a dog, any of that stuff is subjective and created by a human. The vector space embedding does away with all of that and doesn't require those subjective decisions to be made. The fourth thing is that humans need to manually create these taxonomies, which takes time and effort. Again, the vector space skips right past that. The fifth thing is that word similarity cannot be computed easily with the one-hot word representations. So in the vector space embedding, they can. For example, it's just the Euclidean distance between these points. The sixth point is that one-hot vectors become gigantic and unwieldy to make computations with as data set sizes get larger. For example, an English speaker typically has 20,000 words in their vocabulary. So that'd be 20,000 rows in a one-hot matrix. A typical large English natural language database may yield 500,000 different words. And really large databases like Google's 1 terabyte web crawl corpus contains 13 million unique words. You couldn't possibly work with that if you had to have a different row representing every single one of those words in a one-hot representation. Great, so it's clear to me that we should focus on the distributional vector space embedding of words and give no further time to these discrete one-hot representations. Now, the big question I haven't answered yet could be, how do I make word vectors? That is, how do I embed words in a vector space? Well, have no fear. That's what we're covering next.